Sqilah. Enhancing Careers. Chapter 19. Area Navigation System. Area navigation, commonly known as R-NAV, is an aviation method that allows aircraft to fly a direct, customized path between geographic waypoints, rather than being restricted to a zigzag route connecting ground-based radio beacons. R-NAV maximizes airspace efficiency, which results in significantly shorter flight times and reduced fuel consumption. History before R-NAV. In the early days of commercial air transport expansion, a system of air routes was developed to provide a safe means of control and separation of aircraft. These routes, which became known as airways, were defined by radio navigation facilities sited at strategic distances apart and at significant navigational points such as airway intersections, turning points, and FIR boundaries. Pilots were required pilots to fly directly to or from physical ground stations, like VORs, often resulting in longer, inefficient flight paths. By following these airway paths, an aircraft is provided with a system of navigational checkpoints, and, by being enclosed by ATC, in a clear box of airspace, separation from other known aircraft in the vicinity. For many years, the airway system has provided an adequate means of routing aircraft, in spite of the fact that navigation from departure aerodrome to destination is not normally the most direct route. The development of improved and enhanced navigation and communication systems that permit an aeroplane's position to be determined accurately and transmitted speedily to the responsible ATC unit. These enhanced ATC systems make it possible to provide aircraft with safe separation from other air traffic without the need to confine them to narrow corridors of airspace. Add to the above the need to conserve costs, which demand that the shortest route from departure to destination should be followed. To respond to these problems and enhanced capabilities, a system known as Area Navigation, R-NAV, is being introduced. This is a system of navigation which is not dependent upon routing between points which are coincident with the position of a radio facility, but is capable of providing navigational guidance along other non-airway routes marked by waypoints. A waypoint is a predetermined geographic position. This is defined in terms of latitude and longitude, but, where appropriate, may also be defined as a radial and range from VOR/DME beacons. This is known as ρ/θ system, or by ranges from two DME beacons, known as ρ/ρ. R-NAV solves this using an onboard computer, known as a flight management system, FMS. This computer uses a combination of data sources to calculate the aircraft's position and draw a straight line between customized virtual waypoints. Satellite navigation, GNSS/GPS. The most common modern method, providing precise global coordinates. Ground-based stations, using distances and radials from traditional VHF omnidirectional radio range, VOR, and distance measuring equipment, DME, stations. Self-contained systems. Inertial navigation systems, INS, that track the aircraft's movement from a known starting point. Key benefits of R-NAV are direct routing. Planes fly from point A to point B directly, reducing mileage and saving jet fuel. Airspace efficiency. Allows for streamlined arrival and departure procedures, and allows more planes to safely occupy the same airspace. Expanded accessibility. Facilitates instrument landings and approaches at airports that don't have their own physical radio navigation equipment. Subject to an aeroplane being properly equipped, area navigation will be available as follows. Fixed published R-NAV routes. These can be nominated in a flight plan only if the aeroplane is fitted with an approved R-NAV capability. Contingency R-NAV routes. Published routes usable by suitably equipped aeroplanes during specified times. Random R-NAV routes. Unpublished routes. These may be flight planned within designated areas. Area navigation concepts. JAR OPS 1 requires that an aeroplane's navigation equipment should include an area navigation system when area navigation is required for the route being flown. There are three types of area navigation systems: internal system or self-contained system. Systems where the information is derived from airborne navigation equipment, which is a self-contained system. It is a navigation system that is independent of any external information source. A typical self-contained navigational system will use the outputs from an inertial reference system, IRS. Inertial navigation is completely independent of any external visual or electronic reference. It simply updates the position of the aircraft by sensing its accelerations and integrating those, with respect to time, to establish distance and direction of movement from the start position. An integral navigation computer carries out all related navigation calculations. Externally referenced system. This is the system in which information from an external source, or sources, is required in order to provide navigational guidance. Hybrid system. This is the system that uses information from a selection of self-contained and externally referenced navigation systems. Many commercial operators have been quick to realize the benefits of such a system and are not only specifying a suitable system for new aeroplanes, but are, at considerable cost, actively retrofitting their older fleets with similar equipment. Most equipment installations on commercial aeroplanes will form an integral part of a comprehensive avionics package and will be capable of providing area navigation even when out of range of ground-based navigation facilities. Such systems will normally be of the hybrid types. Most modern general aviation aeroplanes are fitted with a basic R-NAV, BR-NAV system as standard. These are generally based on the rho/theta or rho/rho system using inputs from VOR/DME. However, GNSS, the Global Navigation Satellite System, which is based on satellite navigation, will be increasingly utilized as the prime source for the required navigation information. Accuracy of R-NAV equipment. There are two types of R-NAV based on accuracy. Basic R-NAV. The lateral track keeping accuracy of basic R-NAV is plus or minus 5 nautical miles for 95% of the flight time. Precision R-NAV. The lateral track keeping accuracy of precision R-NAV is plus or minus 1 nautical mile for 95% of the flight time. The track keeping accuracy is dependent on the navigation system error and flight technical error. For obstacle clearance, the flight technical error is departure, plus or minus 0.5 nautical miles. At the DR, a value of plus or minus 0.1 nautical mile is assumed. Initial and intermediate climb, plus or minus 1 nautical mile. En route, 2 nautical miles. Basic R-NAV. VOR/DME-based area navigation is a navigation and guidance system which uses basic signal inputs to compute track and distance to a waypoint. VOR bearings and DME slant ranging providing the required information. In some more sophisticated systems, barometric altitude input may also be provided. A block diagram of a simple navigation system is shown below. The simple system, most commonly installed in general aviation aircraft, usually consists of a computer within which each waypoint is defined as a radial and range from a VOR/DME. Such waypoints are often called phantom or ghost stations. The computer's memory is able to store a limited number of successive waypoints, normally a maximum of 9, so that the pilot can enter the planned route before departure. A more sophisticated system will utilize a navigational database stored either within the navigation computer or in an external storage unit. The navigational database contains all the necessary information regarding routes between airports, VOR/DME stations, and waypoints. It is obviously important that this database is kept up to date. It will be updated every 28 days. The Control Display Unit, CDU, is used to enter information into the computer and to display navigation information. In a basic system, the navigation computer resolves the navigation problem. This receives a radial from the VOR receiver, DME distance from the DME interrogator, and altitude from the encoding altimeter. These parameters are used to establish the aeroplane's current position. This is compared to the position of the next waypoint, and an error signal is generated which is used to provide steering signals to a course deviation indicator, CDI, horizontal situation indicator, HSI, or other suitable display. A distance to go is also derived. In some aircraft installations, the computer may also send track correction signals, lateral steering commands, to the autopilot roll channel. Since the use of area navigation systems permits waypoints to be accurately defined, determined, and flown, the need to follow the facility-determined structure of the airways is removed, and this permits direct routing and more effective use of the available airspace. The aircraft equipment will consist of the normal VOR/DME receivers, a navigation, course line, computer, and a simple interface display. Use of basic R-NAV. When operating the course line computer, the pilot selects a VOR/DME station that is within the line of sight range of the desired waypoint. The radial and distance from the station to the desired waypoint is then manually entered. This can be repeated for a number of waypoints, if the equipment permits. Once the waypoint information is stored, the pilot can select the sector, waypoint from and to, and the course deviation indicator will act as if a VOR radial has been selected. You should note that it is possible to select sectors that do not connect successive waypoints. This allows waypoints to be bypassed. Start navigating in the same manner as you would when tracking a VOR station. Distance to go will appear in the normal display. With area navigation, the amount of CDI needle deflection does not vary with distance to the waypoint as it would when tracking inbound to a VOR. It always represents a constant distance off track for a given deflection. On a 5.CDI, 1 deflection equals 1 mile of deviation, regardless of the distance to the waypoint. VOR-DME-based R-NAV has several applications. You can file a R-NAV route flight plan. You get the opportunity of tracking a direct route, subject to ATC restrictions and requirements. You can navigate directly to an intersection, bypassing waypoints. You can set up a holding pattern when the ATC instructs you to hold at present position. You can locate and approach an airfield that is not equipped with navigation aids. The plate shown here is the Oklahoma R-NAV approach procedure in which all waypoints are given both in terms of radial/distance from the Oklahoma City VOR/DME and latitude/longitude. The chart is shown for information purposes only. When using the R-NAV approach mode, the system sensitivity is multiplied by 4. This means that, on the CDI, each dot represents a linear displacement of 1/4 of a nautical mile. R-NAV limitations. The VOR/DME-based BR-NAV suffers the dependent limitations of VOR/DME equipment. If this signal is lost and the nav warning flags appear on the CDI or HSI, you must use an alternative method of navigation. You may fly the area navigation route, using guidance signals to the waypoint, only as long as the aircraft is within the operational range of the appropriate VOR/DME station. The practical range limit is around 200 nautical miles from the associated VOR/DME at the highest altitudes normally used for civil aviation, but remember that the range limit for a light aeroplane will normally be considerably lower because of operational altitude. The accuracy of the position information and any derived steering signals is affected by the same sources of error as the VOR/DME in use. Some systems use DME/DME navigation, with frequency scanning DME interrogators. Such systems provide a more accurate navigation. All other area navigation systems that are dependent upon a single type of source, whether self-contained or facility-dependent, will be affected by the errors of that source. A hybrid system, in which the data from a number of sources is electronically compared and the best information is used, tends to provide a higher and more consistent degree of accuracy. R-NAV versus RNP. The term performance-based navigation, PBN, encapsulates both R-NAV and RNP, required navigation performance, operations. The main difference is that RNP requires onboard monitoring and alerting systems to ensure the aircraft stays strictly within a specific boundary or tunnel in the air, whereas basic R-NAV does not mandate this continuous monitoring.